So there's one thing I'll just add to what I was saying last time, because there was a question we had afterwards. So the question was, why aren't all of these complexes trivial? Because it looks as if it's generated by V. And the answer, for those who are familiar with A modules, is precisely that you can only really think of this as freely generated by V if V is living inside cocycles. So if D is 0 on V. So if D is 0 on V, then yes, that would completely determine the structure of this as an A module. But the point is, once we've got D plus omega, it's not 0 on V. So that's how we're getting non-trivial things there. So now, what I'm going to do for the next example is look at what happens that the DGLA Sehoin was looking at, which was where we had, I suppose I'm going to have to, my notation has been in conflict, hasn't it? Right, so we're going to have I was using, yeah, I'm going to call this C. So we have C in the associative algebra. Actually, I'll call it R for ring. But R was the base. Is it okay if I use R? So, an associative algebra. And then, so the DGLA was shifted Hochschild cochains. The right number, isn't it? So that is 1 with just another bracket. And be coming from as you saw last time. So now let's look at what this gives us. When we input a DG Artinian ring. We've got omega in L1 plus I tensor AI. Definition is that, and this is our sum. So now we actually end up getting, so the purposes of Sehoin's talk, it didn't really matter what happened, so how far down this way. You only really cared about L1, L2, and a little bit of L0. But here, because of the way we're doing this, we're going to get slightly different answers depending on whether or not we have L minus 1. But I'll cross that when we come to it. So let's look at I'll start with the structures we get for non-negative I. So we've got omega 2 as a map from V tensor V tensor MA. And then we get omega 3. Right, generally omega N. So it's going to take N inputs and spit out something in V tensor with the nth degree of A. And so the question is, what's the Malloy-Cantor condition giving us in this case? So what happens is I'm going to first look at this where A is just so dg plus 1, so stops at A0. So in that case we get omega 2, omega 3, and so on. So if we look at V tensor A, and we have multiplication mu plus omega 2, so that gives us a new product. So that deforms the product. Because if we look at mod MA, we're just getting back mu, so it's deforming it. The problem is, if you work out what this lot's giving you, so before, when we just had something here at degree 0, this condition would have told you, all you would have had here is omega 2. Sorry, that's not N there, that's N minus 2. That is important. So in the underived setting, all you had was omega 2. So all these other things didn't exist. And in that case, omega 2 is coming out as associative. But here, it's not actually going to be associative. What happens is omega 2 is associative to a homotopy. Given by omega 3. So if we look at or rather, let's just look at we can linearize. Yeah. So what's happening is that omega 3 is giving me difference between if I know you want u v w, roughly speaking, giving me dot v w minus I've remembered this right, but so, and then that in turn satisfies further relations and so on. And what's happening is V tensor A is what's called an A infinity algebra. Actually, have I just completely messed up the definition of A infinity algebra? Is the issue the associativity or is it the interaction of the chain map? Yeah.
So, what is omega y? Omega y is a differential?
So it would be, yes. So just for now, yes, I think this is it. So for now, I am just putting this restriction here in. So that's going to mean that I don't have omega 1 or omega 0 at the moment. In general, I might do, and I will talk about them imminently. But for now, so last time we saw, Stefan mentioned about L infinity algebras. Yeah.
So is there omega 2 as well on the right side of the roughly equal to?
Over here.
This multiplication, that's
This multiplication is where dot is mu plus omega 2. Yeah. And so it's basically this. And the idea is, so you've seen L infinity algebras. This is the equivalent idea for associative algebras. And yeah, I thought I was safe giving you the first step. I'm not going to try to write down the higher ones. There are clean ways of doing it with causal duality. Yeah, that's what I'll do. I'll give you the causal dual definition, which is direct sum. Oh no, but there's a shift. So if you look at this thing, where you have to make, I might be able to fill in the shift in due course. So we look at this, we have mu plus omega on. So we think of this thing as co-free co-algebra. If that's making your brain explode, just dualize everything. And think of this as a free algebra. So you have a free algebra, and where you define a co-differential defined by this on co-generators. So, whereas with algebras you have to say what you do on generators, how you map from generators. Co-algebras you have to say how you map to co-generators. So you have to say what maps to V. And we have all these omega n's mapping to V. And the point is that it's then the condition that this squares to 0. So it's the Marot-Cantor condition is just saying that squares to 0. So this is giving you a causal dual e.g. co-algebra. And now I need to work out what that sign would be. Multiplication 1.
You mean the shift if it's plus or minus?
Yeah.
It's plus.
Yeah. Okay, so and then, in fact, there's a dual construction you can do for this. Given any, because it's not just this is a technical detail I didn't think I was going to get into. It's not just a DG algebra, because there's a sum here. It's nilpotent, co-nilpotent, and then there's a dual construction you can do that gives you back a DG algebra. So this is actually this ends up giving you back a DG algebra, which mod the maximal ideal is quasi-isomorphic to the one you started with. So it gives you some big free DG algebra. Yeah, I suppose if you kill that, it's giving you a big free associative resolution of the algebra you started with, and then deforming it is what's happening here. And then having really dug myself into a hole and given you the whole Hochschild complex. So MCLA is A infinity deformations. So, by which I mean A infinity structures on R tensor A, such that when you reduce mod MA, you just get back R. So it's that. Now, what about, so if A is actually in DGR, things, yeah, so this is where this example actually becomes so there are 2 extra bits of data we get. Omega 1 and omega 0. Now, in almost any example you work with, this omega 1 thing appears. But omega 0 is a bit special to associative algebras. So, in the case of omega 1, it forms the differential. So that's that. And that's just incorporating the thing we saw earlier with where we were just starting with endomorphisms of V, that if we were starting with some DG-Artinian ring in non-negative chain degrees, there was nothing happening. There was no non-trivial way to deform that. But once we start getting negative degrees, there are non-trivial ways of deforming the differential compatibly. So again, that's still linear infinity different deformations. Now, if we declare that the Hochschild complex starts at C1, that's the whole story. If we incorporate C0, omega 0 is something called curvature. So it's an element in it's just an element. It's not an operator anymore because it's got 0 inputs. And what that means is we don't get d squared is 0 anymore. We get decomposed with d. So it's and that's treat this very much as an aside. That's just so in fact if you want the full, so in the case of this DG algebra, if we're including the -1 term in the DG algebra, we actually get curved alinear infinity deformations. But that is somewhat atypical. So if we'd taken if instead of associative algebras, I'd taken commutative algebras, I could have written down the Harrison complex, which is where instead of taking tensor powers there, you take effectively a free-graded Lie coalgebra. So it's you mod out by actually by shuffles. But there you never have that extra -1 term. So deforming commutative things, you never have to worry about this stuff with curvature. Likewise, any other algebraic structure, we could have done something similar, and it's just this curvature. It's to do with inner automorphisms. Or so it's two categorical structure creeping in. Right. So there are at least infinitely many examples of this form where you pick some other algebraic structure you want to study and you just write down the corresponding complex, and exactly the same sorts of things happen. And likewise, if you're interested in, say you want to do algebraic geometry and you have sheaves of various types of algebras, there are ways of taking derived clonal sections in such a way that you end up with a TGV algebra again. And these things end up incorporating gluing data. And so it's telling you how to deform that sheaf. But for now, I'll stick with the example we've seen and press ahead with sort of what's the point of these derived? Yeah, so what do we get from?
Jon?
Yeah.
What is the gauge group here? Is it homotopic to identity morphisms?
Oh, okay. Yes. So
And just say a word. I think this goes beyond.
So and then all depth would be modulo. In the curve case, it's getting pretty horrible.
I can imagine that.
But it's basically modulo. So if we don't have a curvature, it's modulo quasi-isomorphisms,
Yes.
which are actually anything, or even actually we're working mod that. So yeah. So it's modulo infinitesimal isomorphisms or whatever.
Yes.
But it's doing the right thing. and that's all you really want to know.
Yeah.
Yeah.
Can you say like one word about what the infinitesimal means here?
Oh, so just trivial mod the
Yeah.
So that's the. Okay. So what do we get from? We've shown that we can extend these functors here, and sometimes people talk about about intersection theory at this point. But historically, that actually hasn't been a huge source of examples. So the idea there, and I will just say a little bit, is that once you're working with DG algebras, you can do things like derived tensor products, and that means you can do non-transverse intersections without losing information. And so that's quite often given as motivation, although it's been quite slow to actually be used in practice. But what was really originally the motivation, actually remains the most useful thing, is obstruction theory. So the idea here is you look at small extensions of Martinian rings. So say that surjection of DGI, so local DGI rings small if the kernel I satisfies I times the maximal ideal is 0. And so, simple example you've already seen is where you look at successive truncations of the polynomial ring. And these are the things that deformation theorists study all the time, because typically what happens is you have some algebraic structure. So in the case of a power series ring, and you're starting with something over K, you want to get something over the power series ring, and you work your way up step by step. So you get to this stage, you want to get to that stage. So say we've got say we have a nice functor. Now, rather than being just Martinian rings, and typically this will be one of the sorts of functions we've seen so far. So you're trying to classify some sort of algebraic or geometric structures. You've got them over B, you want to get them over A. And an element in F of B when can we lift? X tilde in F of A. So we want to know when does X lie in the image from F of A to F of B. Now, so if I meant to ask, is this, in the case of Maroc-Canton, I'm not stealing from anyone else's talk at this point if I say what happens here, am I? No. Okay. Right. So if F is a Maroc-Canton functor, so we have say we have a Maroc-Canton element, or actually no, better than that, let's do Maroc-Canton, let's do the deformation functor. So we have some Maroc-Canton element values in B, and we want to lift to one with values in A, such that the image is gauge equivalent to the one we started with. So in the case of deforming associative algebras, you'd have some bilinear associative algebra structure. The question you're asking is, do we have an alinear associative algebra structure such that when we reduce mod I, it's isomorphic to the one we started with? We might have to change coordinates, but we want to know whether we can lift like that. So what we do is, so let's take, we've got omega, choose a representative, B, and now we can lift that to an element in L1 tensor of A. If we forget about the equations that satisfy, then the lift does exist, because the map from A to B was surjective. And now what we want to do is look at the obstruction to this being a Malakato element. So we look at that, and it lies in, well, so we certainly know it lies in L2 tensor I. And yeah, so in fact, and so I don't know whether this is originally due to Manetti, but that's certainly a reference. If you look at his either his deformation functors via DGMAs or various. In fact, he's got a book out now. But so it turns out that this element here, which I want to give a name, so it's all over again, lies in the 2L tensor I. And if you, yeah, you might feel like doing this as an exercise. If you do, the hint is rather than just looking at D of all over here, look at yeah, there deliberately isn't a half here. So what's happening is it's this term ends up vanishing, but it's and you absolutely have to use the fact you have a small extension. So you have to use the fact we know this lives in I. So that's the obstruction to lifting it as a Malakato element. But I wanted to know what the obstruction was to lift it as an element of the deformation functor, so up to gauge equivalence. Another lift, any other lift, is of the form omega tilde plus y, the y arbitrary element of L1 tensor I. And then look at the obstruction of omega tilde plus y. So it's the same as the obstruction we started with, plus dy, and then we also pick up a mixed term. But that vanishes because times MA is 0. Y lies in I, double lies in MA. So what's happening is that therefore omega lifts to f of A if and only if class of this obstruction is 0. H2L tensor I. So if you like, we've got a an exact sequence sets like this. And well, I haven't given you the argument, it actually carries on back here as well. So you can lift something from f of b to f of a as long as f of b is mapping to, as long as it's mapping to 0 in here. And so this was all just looking at the underived functors. What's happened is that H2, which you couldn't obviously see from the original functor, is playing a really important role here in telling you whether you can deform things. And in fact, you can, so there's something entirely similar happens for any reasonably nice derived deformation functor. And that's what I'm going to try to explain now. So, definition, and this is Manetti, when was it? So Manetti, 99 did this, but also look back at Schlesinger's conditions, which were in the underived setting back in 68. So Schlesinger was just doing this on plain Artinian rings. So we say that F local DG Artinian to rings to sets is a deformation factor. If following conditions. So if I have suitable diagrams, I'll put the condition in. It's going to be that this first one is a small extension. So if I take a fiber product, apply F, then you see that gives a map to f of A, gives a map to f of C, and they have to agree on f of B. So have a map like that. So this map is surjective. All small extensions. We don't need any conditional on C to B, although there are various variants, but this is the all give equivalent definitions, and this is the most convenient one. So we also said it has to preserve products in the respective categories. And then there's a sort of there's a rider to that which is almost automatic from that, but not quite, which is that K has to be sent to a single point. So if you feed K into here, I think it tells you as to whether it be a point or the empty set. We're going to need it to be a point, otherwise we have a very uninteresting functor, since everything maps down to f of K. And then, so that's the first set of conditions, which are recognised as being very similar to Schlessinger's conditions. And then the second condition is that f of A to f of B is an isomorphism. Of acyclic small extensions. So in other words, we have the kernel I has zero homology, and it's also small. Times n A is zero. And now, from these conditions alone, construct obstruction theories. Right, I will run a bit. There's just about time to explain why. So, given a small extension, A to B, kernel I, let B tilde be the cone of that map from I to A. So if these things are just all in degree zero, this is just a complex with two terms. We've got A in degree zero, I in degree one. In general, you complex looking like that. This is degree zero, that's degree one. And what happens, so if you see that B tilde to B, that's kernel, it's just the cone of I to I. Which is acyclic. So that's an acyclic small extension. So that tells us that f of B tilde is isomorphic to f of B. But now we can do something really quite powerful, because B tilde also has a map to so the picture is just that we've got this lives inside M A. And look at that final product. We look at things in here which map to K in there. Well, B tilde this. If we're looking at things that K in there, that means we're just killing I. So that's a copy of A. So that's and so now condition one they subject onto f of b tilde. And in fact, we can rewrite f of b tilde as an f of b. So what's happened is this theory has given us a map from f of b a plus I1 such that the sheet of it, this is exact. So I'm saying that an element here lifts back to here if and only if it maps to 0 there. So when f was depth L, so that's, and this really is why people started seriously studying derived deformation theory, this phenomenon, because usually working out whether things lift, calculating obstructions in deformation theory is really hard work. Or try to work out what constraints there are on the possible obstructions, anything like that. And derived deformation theory just gives you the entire theory for free. It's just, you know, if you look at any deformation theory paper by the, you know, prior to the mid-90s, they are probably trying very, very hard to construct this map in a given example. Yeah, and that's a sensible place to get a start in 5 minutes over anyway, I think. So.
Let's thank Jon. Are there questions?
Yes. It says FP has a group structure?
No, it's an exact sequence of sets.
Okay.
Exact sequence of sets. So this set on the right has a marked element.
Okay, so it should be a Freiburg sequence.
Yeah, if you like, that's the 5 over 0. Yeah. If you're interested, there is in fact the next stage in the sequence, which you do playing around a bit. So we have this acting transitively on the fibres, and that's because that's PA. If you think about what that is a plus I. And because it's a small extension, the products do match up, so that the multiplications, the ring structures do all match up.
Maybe it's a bit outside the scope, but I know that in the paper of yours I read that you could, for a simplicial Artinian ring, in some sense, you can also form this cone, and then you just, I mean, I had trouble understanding how you would form the cone in that case.
In the simplicial case?
Yeah.
it's a little so. It's a little harder, but it's basically dot con. You can via dot con you can get the cone as a simplicial abelian group, and then because the product is zero, it's actually not two. So you can quite naturally put a
You just define the product to be zero.
yeah, the product is the product zero on I and just multiplication. But so there is a little bit of work to do, but not much, just because it's still zero.
You don't really have dot con for.
Dot con doesn't behave too well with respect to the ring structure, the multiplication. It's not too bad for associative products. Yeah, there's a surprising amount does survive dot con, but it's a technical dot con type argument where
Okay.
so it's was it somewhere where I was just horribly sketchy?
I'm not sure.
Okay.
I know at some point it was sort of giving this proof, but then for simplicial rings, and then there's this sort of a thing saying, okay, let B twiddle be this fiber product, and then I just couldn't figure out what.
Okay. Yeah, because you. Yeah, I'll double check that reference, but was that in the unifying derived deformation theory?
Yeah, I think so. Yeah.
Okay. Yeah, dot con will work in this case, but yeah, that's right. All you really need to know is the module structure.
Yeah,
and dot con is okay for modules.
okay.
Because it's okay for associative ring. So you form the con via dot con, and then you find you've actually got no choice when it comes to defining